Consider the function f of x equals e to the x squared. Determine the intervals on which f is increasing and the intervals on which f of x is decreasing. So we know a function is increasing when its first derivative is positive, and we know a function is decreasing when its first derivative is negative. So that means the first thing we need to do here is take the derivative of our function. So f prime of x, this is going to be a chain rule. The derivative of the outside function is e to the x squared, and the derivative of the inside function is 2x. If we set this equal to 0, we can find our critical values. E to the x squared will never equal 0, so this part of the function is never going to produce a 0 for us. However, if we set 2x equal to 0, we get a critical value of 0. Now I need to do the first derivative test across my entire domain. And the domain of this function is all real numbers. So my number line I'm going to create is going to go from negative infinity to positive infinity, and you must label your number line because we need to know what you're checking the values on. Then I'm going to plot all my critical values on my number line, and all I had was x equals 0. So we need to see a little bit more than just plus or minuses on this line. We need to actually know that you understand that picking a value in this interval or chunk of the number line is representative of all the numbers on the number line. So you do need to call out what value you chose. So I'm going to pick -1. So when x is -1, f prime of -1 is going to be e to the x squared is always going to be positive, and 2x is going to be negative, so that means we're going to get a number less than 0, because I don't really care about the number, I care about the sign of the number. Over here, I'm going to pick x is equal to 1, so then f prime of 1, I'm going to get a positive value times a positive value, which is in fact positive. So now I simply read my number line and grab my intervals as appropriate. So f, and remember this tells us about the original function f, is increasing from 0 to positive infinity, and it's decreasing from negative infinity to 0. Part B says approximate the integral 1 to 3 f of x dx by a Riemann sum using 4 subintervals of equal length and left endpoints. You do not need to simplify your expression for the Riemann sum. Expressions involving powers of e, such as e to the square root of 2, are acceptable. So the f of x that we're still using is the original one we were given at the beginning of the problem. So since our n is 4, our delta x is going to be b minus a over n, so we get 2/4 or 1/2. This is the width of all of our rectangles. To get the heights of our rectangles, we need to set up our subintervals so we know which values of x to plug into our equation. So if we're using this as our width, we know that the first rectangle starts at 1 and goes to 3/2 because we add 1/2. Then our next rectangle starts at 3/2, we add another half, and so we end up at 2. Our next rectangle will pick up at 2 and go to 5/2. Then our last rectangle will start at 5/2 and end up at 3. So you should have as many subintervals as you do rectangles. This represents the widths of each of our 4 rectangles. This problem told us to use left endpoints, so that means the left side of each interval is what we want to plug in to our sum. So our Riemann sum of 4 subintervals is going to be a width of 1/2 times e to the 1 squared, which is just e to the 1, plus our second value we plug in is going to be e to the 9/4 because we have to square our x's, plus e to the 4th plus e to the 25 over 4. It is also okay if you write 1/2 in each spot, but since they all have the same width, we can write the width out front. Based only on your answer in part A, will your final answer for B be an overestimate or underestimate of the true exact value of our integral? And explain briefly. So we know that the function e to the x squared is increasing on 1 to 3. And if I go back to part A, I absolutely know that, right? I know by looking at the equation those numbers are getting bigger, but we actually found the intervals of decreasing and increasing, and 1 to 3 is right here. So since this function is increasing, I don't have to draw an exact picture of the function, but I know that actually from 0 on, this function's increasing. So if I do left endpoints from 1 to 3, I'm just going to draw 4 little rectangles here, I can see that the rectangles live under the curve. So the endpoints, the left endpoints are giving an underestimate.